tell you the answer if you pay them. And there's this is happening in Europe and also in the United States. And there's also in the that's private sector, but in the public sector, there's all kinds of adaptation planning starting. It's different in different parts of the world, but this is one example in New York City where we had a very bad flood in 2012 due to Hurricane Sandy. And so since then, the Army Corps of Engineers has been trying to put a plan to put some barriers to protect the city. It's not clear if it will happen or not, but there's need for science for projects like this to say what is the risk and how much will the project help. So these are private sector, and the private sector sort of solves its own problem, but with proprietary models. The companies doing these calculations have models that they're selling the results, so they cannot put the data and code on the, open on the internet, because then they won't have anything to sell. So it's a problem to know how good is this stuff really. Are they right or not what they're saying? And this in the public sector needs the same kind of science, but in the public sector, since those decisions will affect the whole population of the country, we really shouldn't be using private information. So there's the whole point of my talk today is to say that we don't have enough science to inform this kind of thing in the public sector. That's why the title of my talk is Usable Climate Risk Science in Academia. Really means academia, university and government. There's a need there, a gap. Okay, so what are we actually talking about? What kind of science do we talk about? So I would argue that basic climate science, as we have come to practice it in every place I have worked and where we do climate science, you can think of it as it's kind of oriented toward IPCC, right? The coupled model intercomparison projects. We take all the observations and the models and we try to understand what's happening with climate change, climate variability. And that's great. I would argue it's really designed to inform mitigation. IPCC is primary purpose is for mitigating, carbon emission reduction. But if people want to do adaptation, they will often want very specific information, and it needs some more stuff in between to be added to that kind of science. And things are downscaling because the global climate models and data sets often don't resolve extreme events, especially very well, and other kinds of, high resolution things. Bias correction, because our models all have biases, systematic errors that are a problem if you want to really use the information for decisions. Impact modeling, so going from hazard to risk means moving from just thinking about the geophysical part to what it's actually going to do to some human system, which we'll talk about in the next slide. And especially a lot of the talk today is going to be about uncertainty. When somebody's going to really make a decision, you have to think about all the things that might be missing or wrong with the science, even if you don't really know how to resolve it. So I'll say a lot more about that, but I think as we've started to do work that's more connected to real world stakeholders, I've spent more and more time thinking about things we don't know instead of things that we do know. Because when you have somebody have to make a decision, you have to tell them about things you don't know, because that affects the real risk. Okay, so the big picture here is that lots of stuff is being done about all of this. I mean, I'm not introducing any new ideas here. This is all things that are being done in many areas, in many countries, in many sectors, but it's not systematic. In other words, I'm trying to say there's something common. There should be something common, some principles or something, some overall science of climate risk for adaptation, but there isn't. People just do this in this sector and do that in that sector, and it's not clear sometimes why you're doing it differently in different ways, or why one way might be better than another way, or anything. So I'm trying to make the case for sort of more organization in this field. Okay. So now, what is climate risk? This is how they think about risk in the insurance industry, and that's how I have come to think about it. So if you have think of a flood, it rains a lot in Sao Paulo and does some damage. There's some loss to someone. How do we think about what causes that? There's the hazard, is the geophysical part. That's how much rain falls and how high does the water get on the ground. Okay. Then there's exposure, which is what is the stuff we are worried about getting damaged. So it could be buildings, could be some infrastructure, could be health of human population, could even be ecosystems. As long as we can put some kind of numbers on it and make a map of it, that's exposure. And then vulnerability, is the thing that tells us if the hazard gets so bad, how much will the damage be to that? So if the water gets this high, I will lose, so much value of my house because it gets damaged. And if the water gets higher, I lose more, etc. So, and then if you can think about that for one event, then you can imagine doing, if you have many events, you can do statistics and say, what's the probability of such and such a loss? What will happen once in a, what's the one that has a 1% probability this year, and so on, if you know the probabilities of the hazard itself. And so again, this is being done by lots of people in lots of different sectors and regions, but you can represent these things at many different scales with different kinds of data. You can do things with physical models. You can do things with empirical, statistical methods. And people just do it one way or another way, and there isn't anything systematic. That's, again, what I'm trying to say. So, but this is what we mean by climate risk, and I'm going to talk mostly about hazard today because I'm a meteorologist, probably like many of you, and so that's what we have worked on the most. But in our research now, we're going towards trying to add exposure and vulnerability and think about how that changes the problem, how that makes a problem with a different structure, different properties. Okay, so let's talk about hazard now, which means, extreme weather in my case. That's what I'm really talking about. So let's say I want to know the probability of some, extreme heat wave or flood or hurricane, a hurricane, very category 3 hurricane that in New York City, which has never happened in the last couple hundred years since we have data. So how do you know the probability of that? You can go and look at the observations, but if it hasn't happened in the last 200 years, then, or in all the data that I have, then you would estimate a probability of 0. But that's probably not right. We know some things can happen which just are rare, and we haven't waited long enough. So that's one problem with using the observations. Another is that even if we had those events represented in the observations, present and future are different than the past because of climate change. So we need some modeling to represent that. So you can go to climate models. Climate models are great. They use physics. Everything happens naturally. You change the CO2, and everything changes by itself using physics as much as possible. But the problems with that are a lot of extreme events are not captured well because of resolution and other reasons, physical parameterizations. They're expensive and hard to use, as you know if you have ever done it. And they do have systematic errors, which in the big picture, if you're thinking about climate mitigation, the biases don't matter that much. I mean, we know that we have a problem with global warming, and the biases won't change that picture. But if you want to really calculate the probability of something in a place, the biases can be a problem. And they don't represent impacts at all. So then there's another way. The insurance industry has developed something called catastrophe models, which you might not know before. They comes originally really from the private sector. And these are designed to estimate extreme weather risk for insurance originally. Now they're used for other things too. And this is a schematic trying to represent what catastrophe models do. They have these pieces: hazard, exposure, vulnerability, and loss. And but how these pieces are put together and some of the problems. The hazard is based on historical data. It's not just historical data, because the catastrophe models or CAT models, I might say, that's the shorthand they use, are designed to solve the problem that the data is not long enough. So you take, let's say you have 100 years of data, you make new events from some statistical Monte Carlo algorithm, make new events that look like the real events, but are a little bit different. So imagine there has been a storm here and a storm here, but never one there. You imagine probably there could be. So put one in between, and it's that kind of thing, but all the algorithms are different. But they're not physical models. They're based on historical data. They're like bootstrapped in the historical data. So that's a problem when you want to do climate change, because the model, at least until recently, these models didn't know anything about the climate they're in, so they can't represent climate change. Now they're trying to put climate in from the outside, but it's a little hard to do that. Also, these models tend to be designed country by country and region by region. So in places where there's not a lot of insurance, they haven't been so well developed. US hurricane is much better modeled than Madagascar hurricane. The exposure and vulnerability data are, in many cases, pretty good, but proprietary. The companies get them from their clients. So they know something about the buildings, they know something about when they have been damaged in the past, but I cannot get that data as an academic researcher, and probably you can't either unless you have some deal with them or you buy it from them. So that's the problem when we want to do public things, open source work. So in our group, what we are doing, I'm going to get to some results now in a minute. We can call it climate condition catastrophe modeling or statistical dynamical downscaling. So I'm making the distinction here that this is work that's kind of trying to take some of the ways people have done things in the insurance industry and the private sector, but adapt it for public use and put in climate change. So we do everything open source and peer reviewed. We're trying to combine what climate models can do, which is model climate change and variability, and what catastrophe models can do, which is a more empirical approach to get extreme event risk and try to combine those. Our model is global. What the model I'm going to show you is all about hurricanes. It's all global, so we're not doing it in just one market or another. And we got motivation on this. Originally, I tried to give credit to Terry Emanuel, who started this kind of work, at least in the academic space. So now get to some work from our actual group. We developed this model, I don't know, now it's almost 10 years ago. We mean Susanna and Michael Tippett and me, and especially Jiaying Li, our excellent young colleague who, when she was a postdoc, wrote this model. So we call it CHAZ, or Columbia Tropical Cyclone Hazard Model. And I'm not going to show you the equations, but it's a statistical dynamical model. So like the CAT model, it generates lots of synthetic hurricanes cheaply with an algorithm that's statistical, but it knows about climate. So what we do is we look at I won't show the equations, but we look at the past hurricanes, the actual data on hurricanes, and gridded data sets, reanalysis data sets that tell us what the climate was, when and where those hurricanes happened. And we do some regression, and based on that, we come up with statistical models to represent how, when and where hurricanes will form, genesis, how they move, and then how their intensity changes every few hours, based on the local climate, a few predictors from the local climate. So then with that, you can take a normal climate model, like a CMIP, coupled atmosphere ocean model, put in your emission scenario, run your model, get your climate change, but you don't believe the hurricanes in here because the resolution is too low. But you take the climate and you put it in our model and generate more your own hurricanes. Lots of tracks here going to some point to the US coast. You can't see the coastline. And then you have lots and lots of storms, so you can estimate the probabilities of rare events that haven't happened. Whether it's right or not, you always have to worry, but at least we can explain how we did it and try to show what the strengths and weaknesses of the approach are. So this is the first actual result I want to show you. This is when we first developed that model, we first did some, wrote some papers using it with reanalysis, just historical climate. But then we wanted to do climate change. That was the whole point. So this was the first time we did that. This paper came out almost 5 years ago, and it's we were downscaling CMIP-5 models, about half a dozen, 5 or 6 CMIP-5 models. And this is the result from that. What it shows is this is time going forward in a particular warming scenario, high warming scenario. And this is the number of tropical cyclones. So actually, this is storms reaching at least tropical storm intensity, 17 meter per second wind speed, surface wind speed. How many on the whole Earth per year? And the black curve is the observations up to some time. And then the different colors are different climate models that we are downscaling. And each one we downscale many, many, many times, many ensemble members. And so we get this solution, which you can see has 2 branches. Some ensemble members have fewer hurricanes in the future, and some have more hurricanes in the future. And it's not because of downscaling different climate models. That's actually the different colors here. But each color has the 2 branches. And what the reason for that is that in our model, we use a bunch of predictors, bunch of different variables from the large-scale climate to tell the model the probability of a new storm forming. And the model is tuned to get the right answer historically. So that's, we trained it that way, so that's not surprising. But one of those predictors is humidity. There's a few others. There's so-called potential intensity, which relates to sea surface temperature and the atmospheric temperature. There's a vertical shear variable that affects hurricanes. But then there's a humidity variable, a sort of column integrated humidity. And we have two versions of our model with two different choices for the column integrated humidity. One is relative humidity, which you know is the actual humidity divided by saturation. And the other is saturation deficit, which is the difference of the same two numbers, absolute and saturation. And if you use relative humidity in the future climate projections doesn't change much. And so that doesn't affect the number of storms, and instead the potential intensity, which is related to the sea surface warming, causes the number of storms to increase. But if you use saturation deficit as your predictor, then as the temperature increases with the same relative humidity, the saturation deficit increases. So the absolute difference between the humidity and the saturation value gets bigger, and that is bad for the hurricanes. So, I mean, the procedure of training the model is objective once you choose the predictors, but you don't know for sure the right way to choose the predictors. And in the past, you can't tell the difference between those two predictors. It looks the same. But under warming, there's no analog to global warming in the historical record. So the bottom line is we don't know which of these is right. We don't know whether we'll have more hurricanes in the future or fewer. And this is our model, which has its own weird, properties. But actually, even if you take the most expensive global climate models, very high resolution ones that can actually simulate hurricanes, also some of them show increases and some of them show decreases. So you wrote a little review article to say that, well, this is our model, but actually this is the state of the science. And this is a big problem for doing hurricane risk because, if you don't have a storm, you don't have any problem. So the number of storms, if you don't know the number of storms, whether it's increasing or decreasing, you have a big uncertainty. And this is something we have to, we don't know how to put probabilities on this. When we try to put probabilities based on history, we get like 50-50, but it's not really very meaningful. So that's one problem. And then in our work with the insurance industry, this is one project sponsored by a reinsurance brokerage firm called Aon. And what they did was they have their own CAT model for hurricanes with their own synthetic storms and their own exposure and vulnerability, which are proprietary. And we take our model, which not only has this global number, but has storm probabilities everywhere. And we tell them how the probabilities of different category storms are changing at each point in the coastline. We give them those changes and they put them in their model, run it through exposure and vulnerability. And this is now percentage change in economic loss from hurricanes in the United States in 2070 compared to history for two different scenarios, SSP 2.4.5 and 3.7.0. This is now CMIP 6, more recent work, downscaling about 12 models. And so it's the percentage change compared to past losses. And there's two solutions here because of the two versions of the model that I just told you. So it's kind of embarrassing. They pay us a whole bunch of money to do research, and we can't even tell them if the sign of the change. But there's still some information there because the magnitude is not very big. I mean, our model, of course, could be wrong about that too, but if you believe it, I mean, these are like 10% changes either way. So it says that if you believe this, then in 20, and this is the average annual loss, 100-year event, 200-year event, etc. That really means the event that has a 1 in 100-year, 1% chance of happening each year. So all of those are less than, this is maybe 20%, okay. But so it just tells you that if you believe this model, then 2070 is not a completely different planet for hurricane risk, and maybe I wouldn't say you don't have to worry about it, and this is for wind loss only. We're not calculating flood here. Flood might get bigger changes, but we haven't done that. Another interesting thing about these results is that these are ensembles of many models, a lot of statistics here. So we have averaged out all the internal variability, or most of it. These are really forced signals. This is due to human activity. And so let's just look at the red branch, the one that gives increasing numbers. So this is an increase due to warming, but this scenario has more warming than this one, but the change is smaller. You wouldn't expect that. It's linear. There could be two reasons for this, and we're not sure why, but we have two ideas. One is it has to do with aerosols. So in this scenario, the 3.7.0, there's more greenhouse gases than this one, but there's also more aerosols. And in the temperature change, all that matters is the total, mostly all that matters is the total force at this level, how many watt meters. But for the hurricanes, it turns out that aerosol and greenhouse gases are different. Aerosols suppress hurricanes and greenhouse gases enhance them, but aerosols are more effective for each watt. In other words, So the aerosols have a bigger impact. So that could be, and we wrote a paper about this. It's interesting physics, but it's because aerosols act in shortwave and greenhouse gas act in longwave. And hurricanes care more about shortwave than longwave. But I'm not going to talk about that anymore unless you ask me, but that's one reason. The other reason has to do, this is for the Atlantic. That's what the U.S. hurricanes come from the Atlantic. And but the Atlantic is affected by the Pacific, and we think part of this difference could be due to how the Pacific responds, and I'm going to talk about that now. So this is some results about the Pacific. So this also started with one of our insurance projects, but has now become a basic research project. So sometimes when you do this applied work, you get ideas for basic research. So in that same project I was just telling you about, we did projections. So this is from the, this is a change. This is a plot of the trend, the linear trend over a 30-year period between starting 2021 in tropical cyclone track density. So the number of storms passing through each grid. And it's averaging, again, many ensemble members. And this is all from the red model here, the one which increases globally. But you see that it's not uniform. It shows big increases in the Pacific and decreases in the Atlantic. So we show this to our friends in the insurance industry, and they know historical statistics very well. They said, okay, you're telling us in the future, your model says there's going to be more hurricanes in the Pacific and less in the Atlantic. But the last 30, 40 years have looked like the opposite of that. Actually, what has happened is there have been much more storms in the Atlantic and fewer in the Western Pacific. So what's going on? Is the past different than the future, or the models are wrong, or what? The Atlantic has some of its own special issues, but because there has been a lot of relative warming in the Atlantic due to aerosols being cleaned up from the Clean Air Act in the United States. But actually, the models know about that, so that should be in there. After we thought about it for a while, we said, okay, look at the sea surface temperature change over that time in the same models. This is what the sea surface temperature trend looks like. So it's warming in the Pacific. So this is global. So it's warming, but the models here are the same as the models here. This is us downscaling the CMIP models, but this is this SST in the models we are downscaling. So it's warming everywhere in the Pacific, but it's warming most here, Eastern Equatorial Pacific. So the trend, the long-term trend in SST in these models, in these projections, looks like El Nino-like trend. And maybe that's why the models are doing this, because in El Nino, we know that roughly, it's a little more complicated than this, but this doesn't exactly look like an El Nino, but something like that. The Pacific is more active and the Atlantic is suppressed. So maybe this is why it looks like this. But our colleagues at Columbia, from the group down the hall, Richard Seeger and Mark Kane, Amy Clement, who used to be there, now she's in Miami, have been making an argument for the last 25 years that the models are wrong about this. And it's becoming a more convincing argument because the observations don't look like this at all. So actually, this is models of the future. Now, if you look at the observations from the recent past, as our colleagues are telling us we should do, this is the trend in SST, actually in observations. This is the so-called HADIS SST data set. And not only is this region warming less than the rest of the Pacific, it's actually cooling in absolute terms. It depends a little bit. This is the trend from 1981 to 2020. Depends a little bit which period you take and so on, but you can't really change the way this picture looks. And so this is the trend in track density in the actual observations. And it looks like, again, the opposite of what the models were showing, suppressed in the Pacific and more in the Atlantic. So maybe, maybe this looks different, like the opposite of that, because the SST patterns are also opposite. So why are the models getting the wrong SST trend? Is it because we're comparing the past and the future, or is it because the models are wrong? Well, it's not because we're comparing the past and the future, because this is apples to apples. So this is now a picture just the historical period, comparing CMIP 6 simulations of the historical period. Actually, this is 1950 to 2014. Sorry, I changed the period, but it doesn't really matter. Historical simulations compared with the observed trends. So this is what's shown here is two different metrics of the Pacific sea surface temperature pattern. So this is the east-west gradient. It's the difference on the equator between east and west Pacific. So El Nino would be here, and La Nina would be here. And this is a north-south gradient. It's a difference between the equator and the regions just to the north and south of the Pacific. So then again, El Nino would be here and La Nina would be here. So the observations are in the blue diamonds, and there's 5 different data sets, versions of the observations, because there's uncertainty in the observations too. And they all are different, but they're all in this quadrant. The real trend is La Nina-like. The models are scattered around. The mean is in the El Nino quadrant, and in the future it becomes more in the El Nino quadrant, but in the past this is where it is. So if you want, so one argument has been the models are different than the observations. One thing could be the models are just wrong. They don't know how to respond to CO2 correctly. We're starting to think that's what's the truth. Models have a real problem. But another possibility is it's just internal variability, right? El Ninos and La Ninas come and go, and you try to draw a trend out for a short period. It may just be random noise. But if that's true, then and if the models can do the El Nino and so, right, then some of the models should overlap with the observations. And they do a little bit. So if you want to say the models are not wrong, but it's just internal variability, it's possible. But it doesn't look that likely. There's not much overlap, especially if you believe these things. So that's the kind of problem that, if you believe how to do climate risk science is, if you go back to the beginning, I said you have to downscale and bias correct. If you downscale the climate models, if none of the models looks like the observations, then you're downscaling, how do you calculate risk? How do you calculate probability of anything if your whole model ensemble is not representing reality? You don't know how to, then the probability of what has actually happened looks like 0. So you're missing something. And we don't have an answer for that yet, but here's what we have been working on, and I don't really have time to describe it in detail, I don't think. Well, I try to do it really quickly. So this is work being done by a great postdoc we have named Jingyi Zhou, supervised by Jiaying Li and the rest of us, including Seeger. These are the guys who's been writing about the Pacific bias issue that I told you. It's Seeger's work that led to this this way of looking at the data. Anyway, the hypothesis here is that came from Seeger and colleagues' work, Seeger and Amy Clement and Mark Kane, is that the reason the models are getting the wrong trend in the Pacific is because of the so-called cold tongue double ITCC bias. You guys know this? The climate models, the equatorial cold tongue are too cold, and they get a double ITCC. And that's a mean state bias, but they argue that because of that, the trend is wrong. So there's a connection between the mean bias and the trend. And if that's true, then our idea was, let's force the mean bias to go away as much as we can by just brute force, which is called flux correction. We just put an artificial term to correct the bias. And then if that's what's causing the trend to be wrong, then it should change the trend. So even though you put in a constant term in the flux correction, I'm not really going to describe flux correction, but it's used to be done a lot in coupled modeling. Not done so much anymore, but we're going back to it to deal with the biases. So I think maybe I'll skip this in the interest of time, just to say that the hypothesis is sort of true. If you do flux correction, so you reduce the bias in the mean state, then the trend changes. So this is the SST trend in the original model. This is the model which has less bias, so it's flux corrected. The difference looks like this. So in other words, it supports the idea that the mean bias is the problem, because the trend now looks closer. This is not the total trend, it's the difference. But the model has moved closer to what the observed trend looks like. Which means, the model can still be wrong, of course, but the model could be right, and it could say that some of the model difference from observation is forced response being wrong, and some of it is internal variability. And then, if that's right, then we can downscale this and say, well, it's a sort of storyline. It's an alternate hypothesis to the multi-model ensemble we have that doesn't capture the observations. And that's one approach to handling these deep uncertainties, big uncertainties. Okay, so I want to spend the last a few minutes. This just says, I'll skip that. What this says is that this trend, this difference only lasts a few decades, and then actually it starts to look El Nino-like, which is interesting, and we're still trying to understand what's the real cause. It might be aerosols, it might be something else, but anyway, might eventually be an El Nino-like trend. I want to now switch to, since I started off talking about risk and exposure and vulnerability, I want to spend a few slides on that. So this is a different piece of work where we're moving from hazard to deal with exposure and vulnerability. I'm going to spend the next couple of slides on a paper, results from a paper written by a former postdoc of ours named Jane Baldwin. She's now a faculty member at University of California, Irvine. And this was our group's first work ever that had economics in it, where we predict not just storms, but actual economic loss. And an economist from the World Bank named Brian Walsh helped us do this. So I mentioned vulnerability. Here's an example of a so-called vulnerability curve. In risk modeling, we talk about vulnerability curve. So this is, you can think of this as, say you have a building, right? Let's say this is the vulnerability curve for a building. It doesn't have to be a building, but imagine that it is. And we're talking about wind damage now. So this is the wind speed on the x-axis. The y-axis is the fractional damage. So if you have, winds below 50 knots, then this is in knots. So to get meters per second, you divide by 2. So if you have less than this, then everything is fine, right? The weather is nice, your house is not damaged. And if you have super duper high winds, then your whole house will be destroyed. But in between, there's some monotonic function that tells you what fractional loss you have. And 2 curves are shown here. This is a curve that's made up by Carey Emanuel. But every vulnerability curve has to look like this. It has to be monotonic, because a higher wind has to do more damage than less wind. So you picked a particular functional form, and the different curves are because there's 2 free parameters. The V thresh is where does it start increasing, which value it starts increasing, and half is where does it reach 0.5, which tells you how, those 2 tell you how fast it increases. So different buildings could have different vulnerability curves. When we first started to do this, we didn't want to use made up things. We wanted to do it right. And if you really know about your buildings, then we talked to an expert on wind engineering who had designed vulnerability curves. So please don't read this. And don't try to read this picture. I'm showing it just to show you that it's complicated. That's all I want you to notice. This is Peter Vickery is this wind engineer who designs a lot of vulnerability curves for the insurance industry models. And the idea here is you know about your house, you do computational fluid dynamics on it, you figure out the pressure forces, when will the roof break off, when will the windows break, all that kind of stuff. This is what he told us we should do. And we're doing a study on the Philippines. We want to estimate economic loss for the whole country of the Philippines. It's completely hopeless. I mean, you can't do this because you don't even know what the buildings are in the first place. And even if you did, you can't do this detailed modeling on every building. You have just some gross idea of how stuff is in the country. So instead, what we did is take an exposure data. We used this vulnerability curve and just guess the parameters and then tune them afterward based on the results, comparing real events. And we use an exposure data set where we don't know about the buildings. We can't get that data. We don't have a data set that tells us all the buildings in the Philippines, or even the United States, actually. But this is a data set that comes from a Swiss group, David Bresch's group, Zurich, and they take gross domestic product, economic data for the country, and they downscale it within the country to 1 kilometer using night light from space. So it's public, data set. So we did that for the Philippines, and here's what Jane did. So first takes some storm tracks, and now this is, now we're doing it from our model, but in this study we did from real storms because we want to compare it to historical events. So take actual storms, the track, the maximum wind speed, use what's called an empirical wind model to unfold and get the whole wind swath. So you have a maximum wind speed at every point on the track. Then we take, we have a vulnerability curve, and I'll explain in a minute why there's 2 again, but it's Emanuel's form with tuned parameters. And then this is our exposure data set. So it's again based on GDP and nightlight from space. And you can see that most of the value is here. This is Manila area. So that's capital. It's where most value is. And just to add a couple things, this is work done with the World Bank. They helped us with the economics. That's Jane. And what she did is first try to, so she do this for all the historical storms we have going back. I don't remember how far it was, maybe 1950 or 1980. I can't remember, maybe Susanna remembers. But anyway, some historical few decades of storms. Calculate the loss with a guess for the vulnerability curve parameters, and then do it again and again and again for many guesses and see how close you can get to the observations. And first, she tried to do it with, we don't have that many storms to fit many parameters. So first tried with one vulnerability curve for the whole country. That's 2 parameters to fit. And when you do that, this is a metric. So then she compares the losses for all the storms. It's called the EMDAT database that gives you loss that actually happened. I mean, it's not perfect data set, but it's the best we have. So how much was actually lost and what is the damage? And by the way, one of the things is we are only calculating wind damage, but we're comparing to all the damage. So we're missing flood information. So we're using wind as a proxy for flood. So that's part of the problem. But you get a different statistics of how good is your result. And there's different ways you can compare. You can use root mean squared or other things. This is called the total damage ratio. It's a metric that compares, that emphasizes the heavy events. So red means we are overestimating the loss, and blue means we are underestimating the loss. And this is the best result you can get with one vulnerability curve. And then we realized, well, the problem is you have way too much loss up here, where the Manila state in Luzon. And if you tune the parameters down to get this right, you'll get not enough loss here. And we eventually realized the problem is that Manila has just stronger buildings than the rest of the country because there's more money, more concrete and steel and so on. And the World Bank had actually household survey data we could use to kind of inform our understanding of that. So she instead went to 2 vulnerability curves, one for the whole country except the state of Manila. It's called NCR. I don't remember what it stands for. National. Sorry, this is the rest of the country. And this is Eastern Visayas. Other way around. This is the whole country. This is Manila. Lower vulnerability. So when you do that, you can get better results. So that's the result of this paper. It's, we're going forward. We're now trying to do climate change and apply it to other regions and think how it relates to policy. This paper was just our first attempt to do it. So there's no big breakthrough here. It's just to show the kind of things you have to do when you don't have all the data you want. You do some things with physics, some things with empirical modeling, some things are guessing. That's kind of this is typical of this kind of work. The compromises will be different depending which problem you are doing, but this is the kind of thing that you see a lot in applied climate risk science. So I want to show one more very different example. Just remember what we were doing here. We're looking at one country, looking at each storm, counting up, trying to add up the losses. I think now you want to estimate, now add to hurricanes, add, fire and flood and, extreme heat, and now do the whole world and estimate what's the cost of climate change. It would be very complicated, right? There are models that do that. This is one of the early ones that tries to do that in a much simpler way. So this is one equation and caption from a paper by Bill Nordhaus from what's called the DICE model. Very different type of model. It's called integrated assessment model that was designed originally in the 90s to calculate the economic cost of climate change to the whole world economy. So I would argue this is still a climate risk model, but it's much, much, much simpler in the sense that the hazard is just one number per year, global mean surface temperature. Everything else is just implicit in that. Doesn't know about the storms, doesn't know about different countries even necessarily. The exposure is just the whole world economy. And the vulnerability curve is also a made-up curve. In this case, it's a quadratic form. This is the vulnerability curve. It's has one term that's linear temperature and one term that's quadratic. So my point of showing this, there are now much more complicated models for doing this. In US, we use them for what's called the social cost of carbon, estimate the policy impact of carbon emissions. But these simple models are still used. You can run in a spreadsheet. And my point is just to show how different, as I said at the beginning, people do this kind of thing at very different scales, in very different applications, very different levels of complexity. This is just to make that point, to compare this to what I showed you one slide before. So I'm now getting close to the end, but I have a few more things I want to say. So here's a summary of everything so far, and then I have one or two more short slides. So to summarize, I've tried to give you an overview of the type of work, and then I gave you a bunch of examples which are much more specific and detailed about hurricanes. But I've tried to make these points. One is that in climate risk modeling, you can do a lot of different kinds of hazard. You can have global mean surface temperature, super simple, or individual storms, much more complicated. You can have many levels of space and time resolution, right? Think of all those detailed storm tracks versus just one number for the whole planet. Also, you can, we've talked about empirical models, physical models, different time frames, different types of decisions, right? Estimating the policy impact of carbon emissions is different than pricing insurance. A totally different application, but the same structure of the problem underneath it. Exposure, we talked about different exposure, actual individual houses or night lights or everything in the whole planet at once. Vulnerability, you can know about your buildings or you can not know about them, it's just guessing. I talked a lot about uncertainties. Some are what we call epistemic or also called deep uncertainties, meaning you can't count how many models do each thing or how many ensemble members do each thing and estimate probability because you don't know if the whole ensemble may be missing the truth. Although I only mentioned at the beginning, a lot of the work that's being done on all this stuff is being done in the private sector now by consulting and financial firms and startups and so on with proprietary models where you cannot easily find out how they're doing everything. Oh, it's AI, we can do high resolution, whatever. Maybe it's good, maybe it's bad, you don't know. But anyway, we shouldn't make public decisions based on that because then if people's lives will be affected in a democratic society, we should know how the decision was made. This is applied work. So as we're working with insurance industry, other people are working with other kinds of stakeholders or users. So they need to get an answer in some time frame on some kind of budget. So you do what you have to do to get an answer. You don't always have the data. You make something up. You do the best you can. But what I'm arguing here is we need to sort of step back and think of this as a field. What is the same in these different kinds of problems? What is different? And what's the consequences of doing it differently? So if you have more money or more computer time, would you add resolution? Would you add physics? Would you invest in observations? How would you change the structure of the problem? So almost the end. In climate science, in geophysical fluid dynamics, which I was trained originally, and probably some of you were too, we have Isaac Held wrote a great paper 20 years ago about the hierarchy of models, which means that in our field, it's not a laboratory science. We can't do experiments, right? We can't change the system and see what happens. So we have to use models, but the models can be wrong, and even when they're right, we don't understand them if they're very complicated. So that's the idea of the hierarchy. And he compared it to biology, where you start with, the bacteria, and then you go to the fruit fly and the mouse, and eventually the person. And at each level, you add more complexity, and you try to understand what changes. So you can start with the real Earth, or the coupled GCM, or the aquaplanet, or a dry dynamical core model that doesn't even have water. And at each level, you see what you can learn. And if you add more complexity, what do you get? I'm trying to make a case that in climate risk modeling, we need that same thing. Now we have vulnerability and exposure and different kinds of empirical and statistical models, but what is the benefit of each level of each degree of freedom? What new do we learn, and how does the answer depend on those choices? So, so my final claim is that somewhere in there should be a synthetic science of climate risk, a subfield that's kind of emerging out of stuff a lot of people are doing, but it needs some synthesis. And I'm trying to make a case. I haven't presented you any overarching theory of this, but I think we should be looking for one. I mean, not a theory to explain everything, but just something to say, what is the structure and what depends on that structure in what way? When we do that, I think we have to deal with the uncertainties that we don't know the answers to, because in basic research, if you have a problem you can't solve, you just change the problem, do the problem you can solve, and you write the paper and everybody's happy. But if somebody has to make a decision, you don't have that luxury, right? You have to tell them the stuff you don't know. So if this is user-driven science, then we have to somehow learn how to deal with that. I didn't talk about ethics really, but because I'm not an expert on it, but I think we have to think about ethics when we think about doing science. Our science could affect where people can own homes on the coast of the United States. So now we have to think about that and how should that affect how we do our science? I don't know, but I think we have to think about it. And everything I'm talking about is user-driven, so you have to talk to users. And my final thing, maybe this is a US-focused argument, or maybe it's not, but because so much is being done in the private sector, I think the private sector actually in some ways is ahead of the public sector, this field. So I'm saying this to make the case that I'm somebody who came from academia and has moved from basic towards applied science. So I'm trying to make the case that we need more of that because the public is depending on us for this information. And we can't just leave it to the private sector to give it to them with proprietary models. So that's everything I have. That's the same conclusions. This is, I didn't mention everybody, but in the talk, I tried to mention some people with this names of at least most of the people at funding. This is a paper I mentioned at the beginning, which makes the case for adaptation science. And we have a podcast too, where I interview people in the field, including Susanna and others. So if you're interested in that kind of thing, it's fun. And that's all. Thank you very much for your attention and for having me here.
Thank you. I love your seminar. I like your seminar.
Thank you.
I don't know what you think. Questions?
I listening to your talk and your final about the electric private sector seems to be ahead of us. And I think this is true here. However, I see here in the field some groups that have been doing a substantial amount of work, good work, in some of these topics related to health. In reading, at least, studying the university, to find that in particular. And here, the university follow open in the economy school, in business, in agriculture. That's actually. I would say that here in Brazil, most of the concern about insurance industries comes from the agribusiness and renewable energy.
Yep.
But you see, from the point of view of electrical energy, 85% electric, wind, solar, and five energy comes from fuel, energy comes from the sea. And I wonder, can you say something about in the U.S. How is the demand for this kind of work in these areas, new energy and agribusiness?
Yeah, I don't know if I can say that much about renewable energy. I'm not an expert in renewable energy and agribusiness. I know a little bit about both of them. I think, first of all, I want to just say again that when I say the private sector is ahead of the public sector, I mean a very specific thing. The public sector and academia is where all the basic science of climate and weather comes from, and everything the private sector does is built on top of that. So they're using the public data and they're adding a layer. And when I say they're ahead of us, I just mean that in the last few years, the private sector has poured a lot of money into that extra layer. And even there's a lot being done in government and academia. So you mentioned in Brazil, that's good groups doing stuff here at the universities. That's true in the United States also. It's just that it's still not enough in the sense that, although if you want the basic data on the state of the atmosphere and ocean, you get it from public sites. You get it from NASA and NOAA and the Weather Service and so on. Everybody does that, private or public sector, they're using public data. But when they want this kind of climate risk data of actual economic impact in some sector, they need this extra stuff. There are some public groups doing it, but it's kind of like nobody's always often sure which data set to use and what the problems are. Like we talked to people from FEMA. I know you asked about renewable and agribusiness, but just to give the example of disaster risk. So FEMA is our federal disaster agency, and towns, when they want to get money from FEMA to deal with disasters, they have to submit a plan. And that plan is now supposed to have something about climate. And they don't know where to get the climate information. There is an academic website, but it's kind of bad and it doesn't really explain. They don't know how to use it. They don't know what its problems are. And so even the federal government is actually even though the federal government has paid for all the basic climate and weather science already, when they need this usable data, they're paying companies again to get it in many cases. And so certainly I know the renewable energy industry, a lot of their data comes from private sector companies. There are firms that specialize in that. I have a good friend who worked in one of them for many years. Because if you want the data that's really going to give you the downscaled predictions of the sun and wind at high resolution for your turbines and solar panels, maybe some university group has done it, but if you reliably want to have it and you want to be sure it's, that you know what you're getting, you're still going to hire private companies in many cases. And I think that's true to some extent in agriculture too. So it's not that the public stuff isn't being done, but there isn't the basic level of, the free data isn't the equal of the private sector data. And it's not just a problem of having stuff to use, but it's also a problem, even if you want to use the private data, because sometimes the private companies, they want to, if they're paying somebody to give it to them, they know they can sort of count on, they can tell the supplier what to do, But it's a problem of knowing how good the private data is, because if it's all proprietary, you don't know exactly how they did it. And it's not really regulated in many cases. Insurance models are sort of regulated, but there's no real oversight. So how do you know what's good or bad if you're not a very sophisticated customer? So it's even a problem for the private companies that are selling the data, because they don't have an incentive to do a better job. Their customers can't even tell. So if we had public models that were good, we would be in better shape. And that's the case in, think of weather forecasting. So if you think of weather forecasting in the United States, that's a different story, because the government produces the weather forecast. The weather forecast is pretty good. It's not perfect. I mean, Europeans are a little bit better than US, whatever, but our weather forecast is pretty good. You can go online and get it from the National Weather Service. Still, there is a private sector doing all kinds of things, adding value, downscaling, giving detailed forecasts, seasonal, whatever, adding their own value on top of that. But because the public baseline is there, there's a standard. It sets a standard. And in this climate risk base, we don't have that. That's the point I'm trying to make.
That comes a bit of a surprise.
Yeah, it is surprising.
It comes as a surprise because my experience, I was director of a national lab. And as director of the national lab, I had to answer for questions coming from the federal government. So we got funding specifically related to things related to this.
Yeah.
In other words, in spite of the fact that the federal government funds research in the area of the world, but they use the national labs to provide information for the government.
Yeah. Well, I think, two things. First of all, I think if you were to talk to the people who run national labs in the United States, they would say that also. I mean, they have plenty of projects where they're advising. So it's not like nothing is being done in the public sector. I don't mean to give that impression. I just think, first of all, it's not enough. Second of all, I think it's people like me who were trained in the basic climate science, or sometimes it's not always connected well to the basic research. So things like these big uncertainties, people just downscale the models, but the user doesn't necessarily know that how the models being downscaled are wrong, maybe wrong in the first place. And it also might be true that this situation could actually be better in Brazil than the United States, because I have seen sometimes, like, I've spent more time in India, but there, so much of the science is oriented toward the monsoon, because they know that's a big problem of the national, of the nation. So I think sometimes in the US, because we have a very big idea of ourselves and we think we're, thinking for the whole world, sometimes we're a little bit, at least in the basic climate science, we're a little bit abstracted from, from those realities. But I also think it's because so much of our field was built up to inform mitigation, to inform the IPCC. And for that, some of these details don't matter. So it's, to some extent, it's the difference between adaptation and mitigation. And it might be that in Brazil, the science is more focused on adaptation than we are.
I think that
It could be.
Okay.
Thank you for a very nice talk. I'm Maria Sobel.
Pleasure to meet you.
I used to be a professor here, and now I am this private sector,
Oh, yes.
the one you were talking about. Thing is, we've got lots of demand on the extremes. How are the extremes going to evolve?
Yeah.
And I thought this was a really nice part of your talk. Congratulations that you're doing that. The private sector is very happy to see these things in the papers and all that.
Thank you.
But I know you'll be talking to us. There's a lot. There's no way a public sector, in my experience, can answer all the
Sure.
That's the way it is, you know.
Sure.
But I see that in the academic sector, things like that, moving into the extremes, now to find the catastrophe model. This is what will really bring and thank you for showing it.
Thank you for the nice comment. I mean, just to be clear, in case I didn't say it clearly, I'm not against the private sector. I think the private sector work is wonderful, and they're hiring all our students and postdocs, and even some senior colleagues. So I think the fact that the private sector has advanced so much in the last 5-10 years is a wonderful thing. It means that people care about climate, that we always said that climate should matter to the capital, the global economy. Now it does. So that's great. It's a job market for us. We are getting funding from the private sector. Everything is good. Yeah, it's just that it's a question of what is the balance, and and you're absolutely right, the public sector cannot do everything, and that's why the private sector has a role. But again, I think the weather forecasting is a good model. Public sector does a basic forecast. The private sector does lots of stuff that the government is not going to do. That's fine. But I think in this climate risk space, which has changed very fast in the last few years, the public sector is underdeveloped, especially because the government itself, certainly in the United States and probably everywhere else too, the government holds a huge amount of climate risk. And for example, if all the private insurers start pulling out of these high-risk states, the states are now holding the risk. The states don't have money, so ultimately they're going to come to the federal government if there's big disasters. So the federal government, that's just one way, but there's many other ways. The federal government holds a huge amount of climate risk. We, the taxpayers, are all on the hook for that. We are all responsible for that. And so we need to understand what we are dealing with. And that the government shouldn't be making decisions based on data they're buying that nobody knows what's in it. There's lots of other, or at least some of it should be public, right? So I'm just saying that it's a question of how much is private and how much is public. And I think the private sector is doing great, but the public sector needs to catch up a little bit, I think. So really, I give this talk to make the argument to my own colleagues in the United States who are interested in this and try and explain what's happening, because if they haven't been connected to the private sector in the last few years, they don't even know it because it's happened so quickly, right? Academia change is very slow compared to the private sector. So 10 years ago, none of this stuff existed, as far as almost none. So it's really a rapid change, and so that's the point.
Pessoal do horário, is there some question
Oh.
in the Google Meet?
How do let's see.
Vamos comentar.
Let's see if I can see.
No, in the chat, maybe.
Oh, this?
No, the net. Yes, open there. No.
No.
Okay, people. Thank you for your assistance and thank you for the
Okay,
presentation.
thank you.
Really well.
So I can quit, I can hang up here.
You close